Okay, this is lesson 4.2, using scatter plots to identify data. In the first lesson, we looked at 4 different displays of data, and in this lesson, we're going to dive deeper into scatter plots. So what is a scatter plot? Well, as we saw last unit, it was how we're going to represent and display 2 variable data. So let's create one on the fly here. It says Shana recorded the costs of customer restaurant bills and the amount they left her as a tip. Whenever you're given a table, if you have your data displayed as like a left and a right, so like a T-chart, the X is always on the left and the Y is always on the right. If it's displayed like this, your X is on top and your Y is on the bottom. And it would never be flipped, and if it was flipped, they would tell you which one is dependent and which one's independent. So in this case, our X values are our bill amounts. That's our independent variable. And our dependent is we're looking to see if the tip depends on how much the bill was. And reasonably, we should say, yeah, it should, because sometimes people tip a percentage, but not always. It might depend on service. So we're going to take a look. So let's see how Shana does here. Shana's tips, we want a title. And our bill amount's going to go on the bottom. And our tip's going to go on the side. So we got our title, we got our axis labels, bill and tip, we got bill, tip, and we need a scale. So let's look at our bills. We got 25, 38, 19, 49, 72. Go all the way up to 72 and as low as 19. So let's start at 0. Let's go up to, I don't know, say 80. Let's go up by tens. So we got 10, 20, 30, 40, 50, 60, 70, 80. We usually use graph paper for this, but I didn't have a grid on here. Just a little practice creating one. I think we've created scatter plots before, but let's give it a shot anyways. Tip. We got to go, our low tip was 250, our high tip was 14, so we got all the way up to 14. Let's do a scale. Let's start at, go up by twos. 2, 4, 6, 8, 10, 12, 14. Is there a reason why I did the ticks on the inside on this one and outside on this one? No, there's not. Realistically, the ticks should probably be on the outside. I don't know why I did them on the inside. Let's graph some points. Our first point is $4 tip on a $25 bill. We're going to approximate here. 25 would be in the middle, 4 would be right here. There's our first point. See, plot the coordinate pair, the ordered pair. We got X, Y. Next point is 38 and 550. 38 is just under 40. 550 be almost up to 6. 19, 27, and 250. That's about 20. 250. 50 and 9. 50, 9's between 8 and 10. 32 and 5. 32, 5. And 72 and 14. 72, 14. That's not bad. It's all approximate. But if we look, we've got a nice scatter plot of points. And it looks like there's a fairly good relationship. Those are almost following a line. That tip was a little low. Let's draw a line of best fit. If you remember how to draw a line of best fit, you want to put your ruler edge so that it goes right through the middle of most of the points. Fairly equal number above and below, but it's really about the distances of the points from the line. Our line does not have to go through the origin. It does not have to go through 0, 0. It just has to go through the points. I drew my line a little high. What are you going to do? That's pretty good. Pretty good line of best fit. That's how we make a scatter plot. We are going to make scatter plots by hand. we are also going to make scatter plots on Google Sheets, and we're going to do both in our assignment. Let's interpret a scatter plot. What information can we gather from it? Jay researched estimates for a job painting his house. The scatter plot below shows Jay's results. Which is the dependent variable? Well, we have hiring a painting company. We got cost on the Y, time required on the X. It looks like our dependent is always going to be our Y, so we have cost. When you see dependent, it's asking you Y axis. Which two companies will take the longest? Which of these two companies is cheaper? Well, time required is on this axis, so if we go to the longest time required, we're here. That would be D and E. Of these two options, which is cheaper? Cheaper would be less cost, so lower. E is the lower one. But E is cheaper. Which two companies charge the same amount of money? Well, so we're looking at the costs being equal. A doesn't have anyone that costs as much. C is kind of the next highest. B and D are on the same cost line. So B and D. And that's how we can get information from a scatter plot. There's more information we can gather from a scatter plot, and it has to do with correlation. There's a lot of different types of correlation. Correlation, as we remember from last lesson, is about strength and direction of a trend or relationship between two variables. So here's all the different ways we can describe correlation. We can call them positive, negative, strong, moderate, or weak. We can choose one of each of these, and we can choose one of each of those. So you could, for example, have something that's both positive and strong, or positive and moderate, or positive and weak. You could have something that's negative and strong, negative and moderate, negative and weak. But you can't have something that's strong and moderate. That doesn't really make any sense. You can't have something that's both positive and negative when it comes to correlation. Positive correlation is where points on the scatter plot go up to the right, and negative is down to the right. So that would look like this, and this one would look like that. Strong means the points are very close to the line. Instead of line of best fit, I'm just going to write LOBF, line of best fit. Strong is what Shayna's tips were. They were all very close to that line of best fit. Moderate is they are kind of close to the line of best fit. And I'm going to show you an example of what these look like. Weak is they are scattered, the points are, but still follow the line of best fit. So let's see some examples of these. Here's 4 graphs. If I draw a line through these dots, whoa, that got really bright there. Our line's going to look like that. And all those points are really close to the line. The fact that we're rising to the right means we have positive. And if I circle the points, look how that circle looks really long and kind of linear, like a line. That means strong. In our second one, our line would be going down to the right. So that would be negative. And if I circle these, they're a little bit more spread out. So we can call that one moderate. In this one, it's really hard to figure out where to draw a line because there's points everywhere. High and low on the left, high and low on the right, high and low in the middle. And if I circle it, I basically just circled the entire graph. That's no correlation. Now this last one, most of the ones on the left are below the middle, and most of the ones on the right are above the middle, and the ones in the middle are kind of scattered. But they kind of are following a line, be it fairly weakly, because those are pretty spread out. So we would call this one, oops, not positive first. We would call this one weak and positive because we're going up to the right. So there's 4 examples. Those aren't the only 4 options. We could have weak and negative. We could have strong negative. We could have weak or moderate positive. Lots of options. Let's do some more interpreting. Davis conducted an experiment comparing a person's leg length and how long it takes them to walk 100 meters. His data is shown in the table on the scatter plot. What sort of relationship does the graph suggest between leg length and time taken to walk? Well, it looks like people with shorter legs take longer to walk than people with longer legs. There appears to be this person here that doesn't really fit the data, but if we were to draw a line of best fit, we might be drawing a line kind of there. So it looks like the relationship is that shorter legs take more time to walk 100 meters, and longer legs take less time. If we have a scatter plot and we draw a line of best fit, we can use our line to make predictions. For example, use a scatter plot to estimate the time it would take a person with a leg length of 85 centimeters to walk. Well, if we have a graph here with 80, that would be 85. Trace up to the line, we end up right here. And if we trace across, it looks like we're just below 65. So maybe we call that 63. Well, maybe 64. 64 seconds. And that's called interpolation. Actually, you know what? That's called extrapolation because that point was further to the right than any other point. We made a prediction beyond the data. If we made a prediction between these points, it would have been called interpolation. Finally, question C says, how might Davis make his results of his experiment more reliable? Now, this kind of goes into experimental design. We'll talk a little bit more about this next unit, but it looks like he's only got a few dots on here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 people. There's a chance that those longer legged people actually were fast walkers, and those shorter legged people were slow walkers. And maybe it's more reasonable that this guy over here is not actually an outlier. Maybe he's just a fast walker with regular legs. What I'm trying to say here is, if you want to make an experiment more reliable, always try to collect as much data as reasonable. So collect more data. If maybe he conducted an experiment on 100 people, he might get a more realistic looking graph, and it might end up looking the same. The relationship might be the same. It might just have more dots around that line, and then that means his line was pretty good. Or maybe there's more people like this person that are fast walkers with medium-like legs, and we might not get as good of a correlation. It's easy to get a strong correlation with limited data. It's harder to get a strong correlation with a lot of data. And that's where it gets really interesting, is when you have a lot of data and you can get a strong correlation. Why is this relevant? Well, it's relevant when you try to consider cause and effect, when you try to decide if something actually causes something else. So when you observe a relationship between two variables, does the correlation mean that one variable causes a change in the other? Now, other factors could be involved, or the correlation could just be merely coincidence. Some relationships are natural and obvious, while others might have a common cause to both variables. Now, a lot of these might take a little bit of research, but we're going to try to use our intuition and kind of make a decision about 3 scenarios here. We're going to state whether each claim is reasonable, and if not, we're going to determine if there's a common cause or if the relationship is coincidental. So it says a scientific study showed a negative correlation between aerobic respiration and blood pressure. It claimed that if you increase aerobic activity, so if you increase aerobic activity, was the cause of the I'm going to try this one again because that did not come out right. A scientific study showed a negative correlation between aerobic exercise and blood pressure. It claimed that if you increase aerobic activity, that would cause a decrease in blood pressure. I don't know why this was so hard to read. Anyways, basically, the scientific study said that if you work out, that caused a decrease in blood pressure. Is that reasonable? Potentially. This is a reasonable cause and effect. Now, there are other things that can decrease your blood pressure, like you could take medication to decrease your blood pressure. But it's also reasonable that there is a link between aerobic activity and a decrease in blood pressure. Mila discovered a positive correlation between ice cream sales and the number of drowning incidents. She warned all her friends not to eat ice cream if they intended to go swimming. So, this is not a reasonable cause and effect. If you eat ice cream, it does not mean that you're going to drown. However, this is an example of a common cause. Because there's a link between why ice cream sales would go up and why drowning incidents would go up. And that link is the weather. When you have hot weather, more people are in the water, therefore there could be more drowning accidents. If you have warm weather, more people are likely to buy ice cream. That's the classic common cause. Last one. Since the 1950s, the concentration of carbon dioxide in the atmosphere has been increasing. Crime rates in most countries have also increased over this time. A newspaper reports that the increase in CO2 level in the atmosphere has caused people to commit crime. This is an example of an unreasonable conclusion. And the reason why is because there are many factors that cause an increase in crime. You could argue that it's also a common cause because in the 1950s, there was less carbon dioxide. There was also less people on Earth. And now, 70 years later, we have more people on Earth, therefore more carbon dioxide in the atmosphere and more people to commit crimes. It's just unreasonable to say that CO2 levels are causing people to commit crimes. Okay, that's it for lesson 4.2. Thanks for watching, and I'll see you in our last lesson, 4.3.